mu, and this gives us what? Actually 1 over n times what? N mu, which will be mu here. Okay? And then let's say also each of them has same variance, say sigma squared, all right? And then we also know the variance of this guy here, x1 plus x2 plus blah blah plus xn over n would equal to what? 1 over n squared times what? N times, okay, so then let me just, so let's say x1 over n give us what? 1 over n squared variance x1, right? Based on the property I just mentioned. So this gives us n squared, then variance sigma squared for x1. For x2, same here, 1 over n squared, sigma squared, plus blah, 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 until what? Last one here, 1 over n squared, sigma squared. This gives us what? Give us sigma squared over n. And then the average among these n random variables, let's say, we call this guy. And this guy would follow a Gaussian distribution with mean is mu here, and the variance will be this guy here. Okay, in other words, you see here, it's possible that we don't know what kind of distribution each of these random variables follow, but the average can be approximated by this what? Gaussian distribution. Okay, so that's the reason why it's very important to study Gaussian distribution. For example, like say in communication system, the signal will be transmitted through a channel, right? Nobody would know, what actually, happened during this transmission. In other words, many noises will be involved in this transmission, right? You can imagine the net noise will be equal to like the average of bunch of noises. And then based on this theory, we say the noise can be modeled as what? Gaussian distribution. Okay? That's the reason why we can say all our communication systems are based on one big assumption, which is what? Gaussian distribution. Okay? That's the reason why it's so important to study, Gaussian distribution. Okay? And here I'm going to show you, like say, if each of these random variables follow this uniform distribution, then the average would follow a Gaussian distribution. You see the difference, right, between this guy and this bell shape, right? So much difference, okay? But the average, we don't need many, we just say 10 of them, okay, would follow a very good approximation of Gaussian, okay? So now, let me show you. I just give you a general idea regarding all those functions and how we can use them to do simulation. Your book actually provides much more information on how to use method to do simulation. Okay, probably that's the reason why this book is chosen for us electrical engineers. Okay, instead of a very pure math book. Have to be less ambitious, just using 1 million number. So otherwise, all right. See, that's what I mentioned before. I'd like to use a combination of math and simulation to teach the class.
So we won't ever have to do any like manual Gaussian.
You need because we cannot use MATLAB to do our test, right? So we still have to understand how to solve some questions manually.
Okay.
Okay. But it won't be very difficult, right? if you understand the concepts. So probably we are going to have midterm after spring break. Okay, it would include chapter 1 and chapter 2. Those 2 chapters.
What chapter is this?
Yeah, we are in chapter 2.
Oh, this is chapter 2.
So,
Okay.
Yes, but we are very close to finish this chapter.
Okay.
Because we're not going to, teach everything in this chapter. Okay. All right. So okay, let's create INDN 1 million. Okay. So let's verify the mean will be very close to 0. Okay. So yeah, it's better than first time, right?
Mm-hmm.
Okay, so I'm happy, so I'm not going to try to be very greedy. So the variance can be determined by the function VAR. It should be very close to 1. So it's very close to 1, right? How about the shape of the PDF? So we can plot this histogram among these 1 million numbers. And then we'd like to use, say, 1,000 beings. In other words, all those numbers, all right, from the minimal to maximum will be divided into 1,000 equal beings. Okay? And the vertical will represent what? The number in each being. Okay? So 1,000 beings. This is the meaning here. See here, right? So at least we see here, this is a bell shape, right? And also you see the mean is here, close to 0 here, right?
Mm-hmm.
I just mentioned this is not actual PDF, okay? And your book tells you how to convert such histogram into actual PDF, okay? And then you can superimpose actually this guy into the approximate PDF. You want to see a very good, corresponding relationship between them. Okay, so the book has a meta script telling you how to convert this guy, okay, into actual PDF. Okay, you just have to read that script file.
Kind of looks like
Okay.
one already.
Yeah, it's already, but it's not because this is, you see, it's a number. You see here, the top is a 4,000, which means 4,000, such numbers. Okay, we have to do something, do some modification. Okay, why don't you just read the script file? Okay, if you have any doubts regarding how it works, just come to see me. We can have some discussion. Okay, self-learning is always important. All right, so here, this is what it's called standard distribution, right? Mean 0, variance is 1. So what if, like, say, we'd like to have a Gauss distribution with mean equal to mu, and the variance is sigma squared? Well, we can create, like, say, x like this, and then if we call this y, then y will be equal to say sigma times x plus what? Mu. Okay, and this transformation will give us this distribution because it's easy to see here, EY equal to what? EY will be equal to E sigma x plus mu, and then linear property give us what? Sigma E x plus E mu, because the mean of x is what? 0. 0 plus what? The mean of const equal to what? Mu. It's mu, right? And then for the variance, y equal to what? Variance sigma x plus mu. And this will give us what? The variance of sigma x plus variance mu. And for a constant, there's no variance, which means this is what? 0, right? And here this is what? Constant. Sigma squared variance x, based on part we just mentioned. This is what? 1, so this is, okay? For example, if you want Gaussian distribution with mean equal to 2 and the variance is 3. Okay? So this is mean. This is sigma squared. Okay, and then we can do the following. So we call this y equal to sigma, which is what? Should be square root 3 times x plus what? 2. Okay? All right, let's test. What's the mean here? So 2, right? How about variance? Y. Let's go to 3, right? Let's also plot its histogram. So take a look at the shape. You see here, it's also what? A bell shape, right? So you see here, right now, the central position is what? Is 2 here, right? Because it's it means 2, and also you see it's kind of like more spread than the normal one here, right? A little bit more. Okay. So that's how we can generate any Gaussian distribution, all right, based on this formula. Okay. All right.
So that's just given to us, or you derive that? The sigma
Of
x
course,
plus.
you have to know both sigma and mu, right? And this x is just corresponding what? This function, right? I have eraser.
I don't know. I don't know what you got.
INDN, right? Yeah. So. Okay, let me just show you here. So x is just a normal distribution, 0, 1, so which means in our case is this guy here, right? So this is our x here, right?
Mm.
Okay. Then you define y based on this x here.
Okay.
All right. If you know the standard deviation and the variance, mean value. Okay. All right. So let's clear everything and let's start over. Now let's create a, say, x1 equal to RA and D, also 1 million. This will be a uniform distribution, okay? So let's plot the histogram. HRST, x1 also 1,000. Okay. So this is, you see here, it's close to a rectangle, right? Okay. Here, figure 1, okay? So let me show you here that x2 also uniform, right? So, and then we define x equal to average between x1 and x2. Okay, and let's open figure 2, and then let's plot histogram for x. All right. So now you see here it's already different, right? It's a triangle. Okay, it could be verified mathematically that the sum of the 2 uniform random variables would give us a triangle distribution at the verse. Actually, this could be done actually using convolution, as a matter of fact.
No.
Okay, so we may touch on this topic later. Okay, after midterm. Okay, you see, everything is useful, right? Just depends on when and where. Okay, even might come to bite you when you are 40-something in a company, right? If you happen to need something. All right, so let's just do step by step. What would happen if we average 3 random variables, x3 equal to same here. Okay, then we define x, right? the average among these three random variables. Okay, that's in figure 3. Also histogram. So that's Windows 3, okay? So we know. You see, it starts to look like what? A bell shape, right? Okay. And let's just create, say, 10 such random variables. And this can be done like this. Let's say we have x1 equal to, it should be okay, because if we have a 1 million by 10 matrix, hopefully it's okay. All right. I and D. So 10 million. So, okay, so 10 rows, and each row has 10 million, sorry, 1 million such numbers. And then, don't get frozen, okay? Yeah. Okay, cool. And then the average among 10 random variables can be done by some function here, because some can be done along different directions. Let's take a look here. So some function, you see, can do this. You see dimension, along dimension, different dimensions. So, and in our case, it should be done by, let's say, should be
1 by 10.
Hold on. So you see, we have 10 rows, right? And then we have to do this average. Let's say along each column, right? Okay, I forgot if it's 1 or 2. Let's try, but we can always. That's the beauty of MATLAB, right? Or Python. So let's say y equal to sum x. Let's say, I'm not sure it's 1 or 2. Okay, if it's 1, let's see what happened here. What's the size? If it's millions, then we end up having right answer. Cool. So which means this will give us the average along each column, right? We do the average, or we do a summation along each column. Okay? And let's divide by 10 average. So it doesn't matter too much, but let's just do it anyway. Okay? And then
Why'd you divide by 6?
because that's average.
Oh, because
It's corresponding, to this guy here, right? All right. As a matter of fact, so I believe, if memory is correct, we can verify. If not, for the uniform distribution, okay, the mean is half. That's for sure. The variance is 1/12. Okay. And then now you see here, which means in our case it's what? It's n is equal to 10, right? Oh yeah. So I made a mistake here. Should be 10. Let's divide. Let's recover. Y times 6 divided by 10. Okay. All right. In our case, n is 10, right? So as a result, in other words, it will be 10, okay? And this should be 10, okay? And the mu should be what? In this case, should be 0.5. And this guy should be what? This guy should be 1/12 times 10, right? Okay? Because the variance is 1/12 for each uniform, okay? And let's verify, okay? Hopefully my memory is correct. Let's put the mean here. So it should be, oh, why is 0.05? What happened? happened here. Let me see here. So it's 0, 1. Oh, hold on. Let me see. Yeah, it should be. Why it's EX1, X2, 10. Yeah, it should be X1, X2, 10. Yeah, it should be 0.5. Why it's 0.05? I don't get it.
Yeah, why doesn't
Let's
nature?
see here. So, y. How about variance? Yeah, it doesn't follow. Yeah, so.
Are you supposed to?
figure out, huh?
You're supposed to sum everything in the column. I think it's just doing just one element in the row.
It should. Okay, hold on. Let me just plot this curve first. Okay, you see what happened. Oh, it's a. Oh no. So let me start over. Histogram 1,000. Yeah, it's a bell shape. Okay. Bell shape. And I'll figure out why. It doesn't follow our theoretical calculation next time. Okay. I guess both of us lose some energy at long day. So based on my voice, you can tell. Okay. You're going to have a chance to kind of verify such a theory. Actually, it's called central limit theory. Okay, and this central limit theory just lays a foundation for the comprehensive application of Gaussian distribution in engineering, especially in electrical engineering. Okay, so that's the reason why Gauss distribution finds such comprehensive applications. Okay, it's based on this central limit theory. Okay, so no matter what kind of distribution it followed at the very beginning, then the average of bunch such random variables will follow a Gaussian distribution. Okay. All right, so I'll fix this difference between theory and simulation, and let you know next time. Okay. Meanwhile, you can also test yourself. Okay. Yes.
So the more, I guess, means that you add up, you went from just a uniform distribution to like a triangular, and then eventually went to Gaussian. Does it always end up going to Gaussian, or that's just?
Yeah, always say
always? Okay.
after you average 10 such random variables, you would have a very good approximation, in terms of Gaussian.
Okay.
All right. Yeah. Actually, we're going to talk about this again. Actually, in chapter number 3. All right. So here, just a first taste of flavor of this central limit theory. Okay. Yes.
About the midterm, so you said is it gonna be right like the week after spring break?
You mean midterm?
Yeah.
Yeah, probably,
Okay.
yes. Okay, we still have some,
Just till next week.
Right. We have probably one more section,
Mm-hmm.
Yeah, but we're gonna skip some, sections.
Okay.
But whenever, for those sections, we don't have any homework, then it won't be included,
Okay.
okay? So
Do we get
you
a
see.
Do we get a sheet on like the equations, or?
Just based on the problem numbers, right? Like chapter 2,
Mm.
6, 1. If 6 is a section number, right?
Okay.
If it's not included, then you don't need to. I'm going to let you know explicitly next time.
Okay.
Okay. All right. So that's all for today. Let's take a break.